Hello, everybody. Sorry for the delay. I'm going to talk about the hardness of data packing. So let us recall what we know about spatial locality. So here's an access pattern example for a program. So you see the temporal locality happens when you access the same data repeatedly closely together in time. However, spatial locality is about data element which is not only accessed closely together in time, but also happens to be stored closely together in space or in memory. But not all programs show this much spatial locality. So we have programs that show poor spatial localities. You don't see good enough spatial locality. So this brings up the question of, are we getting enough of spatial locality? A more quantitative way to ask this question is to say, given a fixed size cache, how does the performance change as we increase the cache block size? So if we take as the performance measure the cache miss ratio, then what we expect is a curve like this. So we are going to rapidly improve the performance, improve the cache miss ratio as we go towards the word size and towards the conventional cache block size. But at some point, we are going to decrease the performance. We are going to incur more misses because we don't have enough cache blocks in the cache. Remember that the cache size is fixed, so we will have a fewer and fewer number of cache blocks. Now, one way to answer the question is to see where that happens, where we actually find a point where we are going to degrade the performance. But this is not the whole picture. So let me read for you this quotation from a MEMSIS paper. When increasing the cache line size from 64 bytes to 128 bytes, the number of misses will be reduced by 10% to 30%, depending on the workload. So these are mobile workloads. However, because of the low cache line utilization, this more than doubles the amount of unused traffic to the L1 caches. So what this implies is that the 10% to 30% improvement is not actually an improvement. This makes sense because when you think about it, when you double the cache block size, you need at least 50% improvement in your cache miss rate to cancel out the effect of the traffic to at least get the same performance as before. So effectively, we are going to look at a point even before that happens. So maybe the answer to the question is a negative answer. Now, what we are going to do in this work is we are going to introduce a framework to analyze how efficient we can improve the spatial locality. And we are going to study the complexity of the problem. So what is the most general problem that we have about? So let me tell you before this that the most important way or the most obvious way to improve spatial locality is by replacing data in the memory, which is called data replacement or placement, data layout, whichever you want to call it. And the most general problem definition is given a sequence of n references to fixed size objects, and everything, all the details of the cache, find a data placement in memory that minimizes the number of cache misses. So this is called the cache-conscious data placement. It's very simple. But it turns out that this simple problem actually is very hard to approximate, even for such a liberal approximation factor. So we cannot get even that close to the optimal solution. Now, what we are going to do is we are going to narrow down this definition to what is suitable for our for what we intend to do, basically the spatial locality. So first, as we inspect PageRank's results, we find out that his hardness result is based on conflict misses, which means that it is very hard to minimize those misses. However, if you think about it, spatial locality does not have much to do. It's not very related to conflict misses. So we are going to first get rid of that complexity. So we are going to assume a fully associative conflict-free cache. And then the first question that comes to our mind is whether these fully associative caches are actually used in practice. So we will have software caches, a lot of software caches that are used. And we also have hardware caches, which are managed with software that either are nearly fully associative or they are fully associative. Even if we look at the conventional caches in hardware, we still find out that a major portion of the misses actually come from capacity misses, not from conflict misses. So on common workloads, 98% of misses for set associative caches actually come from capacity misses. Now, when we assume a fully associative cache, data placement is only important when object sizes, if you assume the same object size for every data object, it only matters when object sizes are smaller than the block size. It also depends on the alignment, but let's not care about alignment for now. So in this work, we are going to assume that the object size is smaller than the cache block size. So let's see how our formulation of the problem looks like now. So data placement for a fully associative cache, we have n references to objects of the same size. P is the packing factor, the number of objects that we can fit in a cache block. And B is the cache block size. So now the data placement is equivalent to a data packing, which means that a solution that specifies which objects we want to group in the same memory blocks. Now, our result is actually basically we extend PageRank's result to our problem. So we prove that for every number of blocks in the cache starting at 5 and every packing factor starting at 2, this problem is NP hard to approximate with such an approximation, even within such an approximation factor. And regarding replacement policies, our result holds for all sensible replacement policies. Sensible replacement policies are defined by PageRank and Rabbits. We adapted this. In high-level terms, it means that when you operate the replacement policy on a loop, then you fall into one of the two cases. Either you have less than m plus q misses. Q is the parameter for the sensible replacement policy. Or you have more than the number of iterations misses. This depends on whether the objects in the loop are actually packed in a total of at most m blocks. M is the number of cache blocks. And it turns out that all well-known replacement policies are zero sensible, actually. So FIFO, LRU, MRU, everything. So it's very hard to come up with a non-sensible replacement policy. Now, the proof strategy is reduction from 3-sat. So given a 3-sat instance on a set of variables and a collection of classes, we are going to separate the cases where we map from a positive instance of the 3-sat and the case where we map from a negative instance of the 3-sat. So we are going to build a gap between the optimal number of misses in the two cases. And when we do that, then we can argue that any approximation algorithm with a factor at least as good as that would place 3-sat in P. So this proves that this proves our theorem. So a little bit details about the construction. So given a 3-sat instance, for every variable, we are going to introduce 3P data objects. We are going to add sequences to the reference sequence. to ensure that if we are mapping from a positive 3-set instance, then the optimal data packing solution packs these objects in one of the two ways. So we associate one, the left one with the variable being assigned to true, and the right one with the variable being assigned to false. Now, this helps us when we encode the sequences for the clauses. Now, for a typical clause, we add this sequence. So the only thing that changes clause to clause is the first line. If a literal is appearing as a positive literal, we are going to add A1. And if it is appearing as a negative clause, as a negative literal, we are going to add C1. And then we add a gamma, which is a sequence over P times M minus 5 objects that we ensure are always packed together if we are mapping from a positive 3-set instance. And now this completes the reduction. Next, we are going to see what happens when we take as the objective value, not minimizing the cache misses, but maximizing the cache hits. So obviously, from the optimization point of view, this is the same problem. But when you think about approximation, it may have different implications. So for example, for a one-block cache, we can formulate the problem as a graph packing problem. This is basically partitioning the proximity graph into sets of bounded size. And the bound is basically the packing factor to maximize the weight of the edges inside partitions. So it's easy for the one-block cache. But for a general number of blocks in the cache, we formulate the problem as the generalization of graph packing, which is hypergraph packing problem. So the hypergraph packing problem is defined as given a collection of weighted sets, which each containing at most p elements, find a collection of disjoint sets in F, which has the maximum total weight. And a simple greedy approach gives the p-factor algorithm for this problem. We're just going to take the biggest element, the heaviest set, or hyper edge, I should say, from this collection over and over again until we are left with no choice to make. And so the only thing that remains is how to assign those weights based on our problem. So we are going to, let's consider the one reference sequence. This is a 2-block cache, and we have a packing factor of 3. The question is how to set the weight of this hyper edge. Now, so let's see. So packing A, B, and C in the same block will potentially give 3 block reuses, which lead to 3 cache hits. But if you look at the first block reuse, and remember that the cache has only 2 blocks, it may only hit in the cache. B may only hit in the cache if U and V are placed in the same memory block. Otherwise, by the time B is accessed, the block that contains B is going to be evicted. So the idea is simple. We are going to consider only the block reuses that the packing guarantees independently from other packings. So when we assign the weights this way, we are going to have the proximity hypergraph, generalizing the proximity graph for the one-block cache. And now we prove that the optimal solution for the original problem is always within a factor m of the optimal packing for the proximity hypergraph. So this factor m is, so it linearly relates to the cache size, so it's not very good from the practical point of view, but we have a theoretical guarantee at least. So overall, we have an approximation factor of m times p, because we are going to use a p-factor approximation algorithm for the hypergraph packing problem, for the cache hit maximization. As future work, we are going to pursue several interesting directions. So first, we are going to see what happens when we restrict the phase behavior. So let us now, for now, assume a very simple definition of phase, which is a loop over distinct objects. Now, it turns out if you look at our reduction, it turns out that our reduction maps to reference sequences with n to the power of epsilon phases for every epsilon. And this means that the hardness will hold even when we are restricted to those instances. So how about when the number of phases follows a smaller function, constant, logarithmic, or polylogarithmic? And we can also change the definition of the phase to come up with a more general argument. The other more interesting direction is that what happens, so let's say I don't want to care for the case when the cache miss ratio is very small. I don't want to do anything about it. I only want to apply data packing when the optimal solution, when I know that the optimal solution is more than a threshold. So remember, we don't have the optimal solution here. So this is called like a promise problem in complexity. And you have this as a promise, but you can't really check this promise. But it's interesting. And the other direction is, this is quite simple. Our algorithm for the cache hit maximization is not very good. It does only guarantee it does give only a theoretical guarantee, but it's not very good in terms of performance. So how can we improve the running time or the approximation factor? Finally, a very interesting thing to consider is data packing for partition cache. So this is very interesting from the practical point of view, whether we can consider coherence misses as well. To conclude, we explained the data packing problem. It's a challenging and important problem for today's block-based, highly associative caches. We formally defined this problem, and we showed the hardness of approximation. And we showed that when aiming at hit maximization instead of the miss minimization, the data packing problem admits a constant factor approximation algorithm. Here are the references, and thank you.
Question? So can you comment on whether your hardness result suggests any algorithm for data layout?
For data layout? So as I said, one way to think about it is to consider the phase behavior. So we can look at our reduction to see what kind of phase behaviors it doesn't allow for efficient approximation. So I gave one case, but there might be also other cases that we can capture from the reduction. So with that simple definition of the phase that I gave, it's simple to come up with the algorithm for the case when we have we have constant number of phases, but our phase definition is very simple. So it's going to be very trivial. But if we want to have positive results, we should probably look more into the algorithm for the cache hit maximization. Sorry, I believe that the algorithm works. I mean, in terms of how close we can get to the optimal solution, I believe it's very good. But still, it's not very good in terms of the running time. So we should do something about that. Thank you.
let's thank the speaker again.
Do you need the dongle?